Welcome back to the wonderful world of math, where the sun is always shining and the math is always exciting. Anyways, today we're going to be talking about inflection points. Now, last lesson, we talked about the idea of concavity, a function being concave up and concave down. So if you remember, concave up is like a cup. So we have a function that might look like this, concave up, or concave down. When we say concave down is like a frown, right? So anything that is trending up would be a function that's concave up. Even if the function is decreasing, it can trend in a manner that's concave up. And the way we talked about that, the way we understood it, the way we interpreted that, is through the eyes of the second derivative. So if we can see that a function is concave up, we know that the second derivative will be positive. And the reason that's the case, if you remember, is that if a function is concave up, that means its derivative is increasing. Its slope is increasing. So you can imagine tangent lines, and as I move this tangent line along as x increases, we can see that the slope is increasing, that the function is getting steeper, or the function is flattening out depending on which side of this minimum we're on. But the bottom line is the slope is increasing. Maybe the slope is -3, and then it goes to -2, and -1, and 0, and then 1, and then 2, and then 3, and so on. In other words, the slope is increasing. The derivative is increasing. Well, if we understand the idea of a function increasing, if the derivative is increasing, then the second derivative must be positive. Okay, so with that in mind, with the idea of concavity under our belts, we move on to this idea of inflection points. Okay, so an inflection point is a point where a function changes concavity in the basic definition. But one thing that we have to be clear on is that there must be a tangent line at that point. And so if we have a graph that looks something like this, it's concave down, okay? And then all of a sudden it turns to being concave up. The point where it changes from concave down to concave up is called the point of inflection. Point of inflection, where the concavity changes. But again, the caveat to this is that there must be a tangent line. You must be able to draw a tangent line. And it could even be a vertical tangent line, as long as you can draw a tangent line. So I can imagine a tangent line, a line that just skims this function here. And actually you can see on a point of inflection, the tangent line, in a sense, kind of passes through the function. But we don't have a point of inflection when we have something that might look like this. So we have concave down, and then all of a sudden it turns to concave up, something like this. Well, concavity changed at this point, but you can't draw a tangent line there. The function's not differentiable, but it's also not a vertical tangent. So we have a corner of some sort here, so there is no point of inflection. So in other words, a point of inflection is when concavity changes, but you can still draw a tangent line. Now with that said, what are we looking for here? The bottom line is, for a point of inflection, we're looking for when the second derivative changes signs. Because if a function is concave up, the second derivative is positive, and if the function is concave down, then the second derivative is negative. So if it's going to change from one type of concavity to another, the second derivative must change signs. But we also have to check to see that the first derivative either exists or it produces a vertical tangent line. So let's go ahead and take a look at an example of this, and we want to identify any types of inflection points, or anywhere the inflection points exist. So we have this function that says y equals e to the negative x squared. And we're trying to find the points of inflection. So we're going to work our way down. We're going to take the first derivative, and the first derivative here needs the chain rule. The derivative of e to the something is e to the same thing, e to the something, and then times the derivative of the something, so times negative 2 x. Okay, so that's our first derivative. Now, what I notice here is that the first derivative exists. There is no points of discontinuity within the first derivative. So we can say that there is a tangent line that can be drawn at all points. So the caveat here of a point of inflection is met, that the tangent line does exist. Now we'll take the second derivative. But before I do that, let me go ahead and rewrite the first derivative so it's a little bit cleaner to see. It's going to say negative 2x times e to the negative x squared. Now to take the second derivative, we have to use the product rule here because we are multiplying two separate functions. So the derivative of the first piece, negative 2x, is negative 2, and then times the second piece, so times e to the negative x squared, plus the derivative of the second piece, which looks awful familiar. It'll be e to the negative x squared times negative 2x, and that's just the derivative of the second piece here, so we have to multiply it by the first thing, so times negative 2x. So I'm going to clean this up, and we're going to say y double prime is equal to negative 2 e to the negative x squared, and then this combines to be plus 4x squared times e to the negative x squared. Now from here, it's always a good idea to get your factored form. But remember, we're looking for when the second derivative changes signs. If the second derivative changes signs, then the function will change concavity. So we would look for when the second derivative changes signs, just like if we're looking for extrema, we would look for when the first derivative changes signs. So the process is pretty much exactly the same. It's just we're looking at the second derivative instead of the first derivative. So we're going to go ahead and factor here. And we notice that we can factor out a negative 2 e to the negative x squared, and then what's left over here is going to be 1 minus 2x squared. And so there's our second derivative. In order to figure out where that function changes signs, we're first going to figure out where the second derivative is equal to 0 and where the second derivative does not exist. In this case, the second derivative always exists because the domain in this case is all real numbers. We're not taking the square root of a negative number. We're not dividing by 0 anywhere. I take that back. We are dividing by 0 at one place, and that's when x equals 0. We'll get that in a second. So we'll set this equal to 0, and we would say that this occurs, this function is equal to 0 when this term is equal to 0 or that term is equal to 0. Well, exponential functions are never equal to 0. So there's no place where it hits 0 here, but this one does. So we're going to set that equal to 0, 1 minus 2x squared. And so we have 2x squared equals 1. And so x squared equals 1/2. And then we'll square root that, so we get x equals plus or minus 1 over rad 2. So that is 2 points where y double prime equals 0. And we also have to consider where y double prime does not exist. Well, y double prime does not exist when x is equal to 0, because if x is equal to 0, I take that back. I take that back. It does exist there. If x is equal to 0, then if x equals 0, then e to the 0 is 1. So that does exist there. So these are my two, I don't want to call them critical points, because critical points are specifically talking about looking for extrema in a sense, but I would call them points of interest or points that are critical but not critical points. But anyways, from here we're going to go ahead and set up a number line dealing with these two x values, so negative 1 over rad 2 and positive 1 over rad 2. We know that these x values produce zeros for the y double prime function, and we want to pick values to the left and to the right of each one of those. So now this is radical 2, so we don't want to think too hard on this. Radical 2 is 1 point something, so negative 1 over 1 point something is going to be a negative value. I'm just going to steer clear of that, and I'm going to pick like negative 10. Negative 10 is less than that value. So negative 10 plugged in here, e to the negative 10 squared. Well, negative 10 squared is a positive, and then this is going to be negative, so negative 100. E to the negative value is always positive. This thing is always positive. And then we're going to multiply it by -2. So this term is a negative. And then when I plug in -10 here, this will be positive times -2 will be negative. And then 1 minus that negative is going to end up being negative. So we have a negative times a negative. So in the first interval, the second derivative is positive. Now for the interval between -1 over rad 2 and 1 over rad 2, I'll pick x equals 0. Well, if I pick 0 here, I've got e to the 0 is 1. -2 times 1 is negative. If I plug in a 0 here, that all goes away. We got a 1 here. So a negative times a positive is a negative. And then we'll plug in a positive value greater than 1 over rad 2. So we'll plug in 10. Negative 10 squared, that's going to be -100 because we have to square the 10 before we take the negative. So -100. E to the negative number is a positive value times -2 is a negative value. So this term is a negative. I plug in a positive 10 there. 10 squared times -2 is -200. 1 minus 200 is a negative. So again, we have a negative times a negative. So we have a positive in this interval. So we can see, based on the second derivative signs, we can see when the function is concave up and concave down. So within this interval, we're concave up. When this interval, we're concave down. And in this interval, we're concave up. So we can maybe draw a little concave up, concave down, concave up idea. But remember, points of inflection are those points for which concavity changes. And that would imply that the second derivative changes signs. Going back up here, the y prime does exist everywhere. So points of inflection are going to be at, let's see, points of inflection. Oh, my marker's dying here. Points of inflection occur when x equals -1 over rad 2 and +1 over rad 2. Okay? Now, in this particular problem, it's saying identify the points. Well, we've identified the x values, but we haven't identified the points yet. So we need to figure out the y values here. So this tends to be a sticking point for students sometimes. It's, where do I plug this x value into? Well, if I'm looking for concavity, I'll plug the x values into y double prime. If I'm looking for whether the function is increasing or decreasing, I'm going to plug my x values into y prime. If I'm looking for the actual coordinates, the actual values of the function, I'm going to take these x values and plug them into y. Well, in this case, I'm looking for the points of inflection. So I'm looking for the actual coordinates. So I'm going to take these values and plug them back in to y, way up at the top there. And so when I plug in -1 over rad 2, we would say y for -1 over rad 2 is going to be e to the -1 over rad 2 squared. And let's see, that simplifies here. 1 over rad 2 squared is going to be 1 squared over rad 2 squared, so that's 1 over 2. And that's going to be a negative there, so it's e to the -1/2. Or we could say that this is going to be 1 over radical e. So we're taking that negative exponent, moving things down, and anything raised to the half power is going to be the square root of e. So one answer is -1 over rad 2, comma, 1 over radical e. So that's one coordinate. And then we're going to go ahead and plug in 1 over rad 2 to the function again. 1 over rad 2. So we get e to the negative, oh, I screwed that up. Let me go back here, but it's really not going to change an answer. In the previous case, I plugged in positive 1 over rad 2, not negative, so we're just going to change this guy to positive 1 over rad 2. And now we'll plug in our negative, so that was our positive value. Now we'll plug in our negative value, so it's negative of -1 over rad 2, and then square that. But again, when we square this, and we're squaring the negative, the result is exactly the same. So our answer ends up being exactly the same, 1 over rad e. So our second answer is -1 over rad 2, comma 1 over rad e. So these are our two coordinates for which we have a point of inflection. Okay, so let's just go over that real fast. What did we do? we said to find a point of inflection, we took the second derivative, and we want to see where that second derivative changes sign, so we set it equal to 0. Found where the second derivative equals 0 at negative 1 over rad 2 and positive 1 over rad 2. We check our number line for our second derivative, plug in values to the left and right of each of those points. We get positive, negative, positive, which gives us our concavity. And we can see that our concavity actually changes signs at those two values. And so we take those values and plug them back into our original function. And we end up with 1 over rad e in both those cases. So our final answers are those two coordinates. Okay? The good thing about the AP Calculus exam is that there's no need to simplify anything. And so we have standard rules in math that say we don't like radicals in the denominator, so we rationalize the denominator. But calculus is kind of beyond that, because a lot of times calculus is about finding actual values that we can go out into the real world and apply. And so we're really looking for decimal answers in the end anyways. So we don't need to simplify all these things here. They'll accept that as a final good answer. All right, so let's go ahead and go on to a problem that's kind of all-encompassing. It's dealing with the ideas of extrema. It's dealing with the ideas of concavity and increasing, decreasing. And as a result of all that, we can also throw in points of inflection there. So we have this problem. It's a good practice problem here, where it gives us f prime of x. So f prime of x is equal to 4x cubed minus 12x squared. So in this problem, we are looking for when we have relative extrema, or absolute extrema for that matter. So if you think back from a few lessons ago, relative extrema occur on a continuous function when the derivative changes signs. Okay, so that's what we need to look for. We need to look for when the derivative changes signs. Well, if you remember, the reason a derivative can change signs, or the places where a derivative can change signs, are when the derivative is equal to 0, when the derivative does not exist, and at endpoints. And if you remember, those were called critical points. So first we identify the critical points, and then we determine if the derivative changes signs at those points. So what we see here is that we're given the derivative. There's no reason to take the derivative because we already have it. Okay? So the first thing we're going to do here, it's always good practice, is to factor, if we can. Since we already have the derivative, we don't need to take it. We'll just factor this. We can factor out a 4x squared. And then what's left when we factor that out is just going to be x minus 3. From here, we're going to find our critical points. So we're going to set f prime equal to 0. And solve that, so we can see that that occurs when x equals 0 and when x equals 3. So we have one set of critical points when the derivative is equal to 0, so at those 2 points. The other critical points are when the derivative does not exist. Well, this is a polynomial function. The derivative always exists. And then the last set of critical points is when we have endpoints. Well, there are no endpoints in this function because this domain includes all real numbers. So these are our only critical points. So from here, we're going to set up our number line. At 0 and at 3, we have zeros for our f prime function. And we're going to go ahead and pick values to the left and to the right of these zeros here. So we're going to plug in negative numbers here. If I plug in any negative number, when I square it, this whole thing becomes positive. And then if I plug in a negative number here, a negative minus 3 is a negative. So positive times a negative is a negative. I'll plug in a number that's between 0 and 3. Maybe I'll plug in 1. So 1 squared is 1 times 4 is 4, so that's positive. And then 1 minus 3 is a negative. So positive times a negative is a negative. And then we'll plug in a number that's greater than 3. So maybe 4. Again, this will always be positive. And then this will be positive here. So just a side note, we can see that the derivative does not change signs at x equals 0. And the reason that's true is because we notice this 0 came from the x squared part of this function. Well, x squared is always going to keep that result a positive number or equal to 0. In other words, this term, the 4x squared, will never be negative. So we won't see a sign change when that exponent is an even number there. So anyways, now we can identify where extrema occur. Remember, at 0, we don't have an extrema. we would say that there is no extrema here. And the reason there is no extrema when x equals 0 is because the derivative does not change signs. So, and then we can also say that there is a relative minimum at x equals 3, and we'll go ahead and justify this. We would say that there's a relative minimum when x equals 3 since f prime changes signs from negative to positive. Now, if I wanted the actual coordinate for that relative minimum, I would then take the x value 3 and plug it back into f of x. But I'm not given f of x here, so I can't do that. So the only thing I can do is identify where the extrema occur, or in other words, for what x values the extrema occur, and that is when x equals 3. Now I could take this one step further, because at x equals 3, this is not just a relative minimum. This is going to be an absolute minimum. And the justification looks like this. First, I'll look at a graph. We can see that f prime is negative, which implies that f is decreasing, and then it kind of flattens out. We end up with a horizontal tangent when x equals 0. And then the function goes and decreases again because the derivative is negative. It flattens out again when x equals 3. And then now the function is increasing to the right of 3. So again, we can see that the function has no relative extrema at x equals 0. We can see that it has a relative minimum here. And because these signs for f prime will continue on, for every value to the left of 0 will be negative, and for every value to the right of 3 will be positive, we can actually see that there's an absolute minimum there. Now let's go ahead and talk about justifying that type of absolute minimum. We would say that there is an absolute minimum when x equals 3, since, now this justification is different. You cannot justify an absolute minimum by just simply saying f prime changes signs at that point. We normally would say for an absolute minimum, well, we'll take that point, or take all our critical points and plug them back into f and just see which one the lowest value is. But in this case, we can't do that. We have a unique case here. We would say since f prime of x is less than or equal to 0 for the interval negative infinity less than x less than 3, and f prime of x is greater than or equal to 0 for 3 is less than x is less than infinity. Okay? So what we're saying here, by justifying it this way, we're saying f prime is 0 for all values, or sorry, f prime is negative or equal to 0 for all values to the left, which means that the function f is decreasing for every value to the left of 3, and then the function is increasing for every value to the right of 3. Since we have a strictly decreasing function to a strictly increasing function at x equals 3, where that changes, we have an absolute minimum. So that answers question number 1 for us. Now we can talk about question number 2. Well, question number 2 is directly related to question number 1. It's asking for when the function is increasing or decreasing. So we can conclude pretty easily here that for question number 2, f is increasing over 3 is less than or equal to x is less than infinity, since f prime is positive over this interval. Okay? Now we can say strictly positive, f prime is positive, because it's not equal to any other value or any other sign, or equal to 0 for any value to the right of 3. But then when we go to talk about f being decreasing, f is decreasing over the interval negative infinity less than x less than or equal to 3, since normally we would just say since f prime is negative over that interval. Well, it's not negative over that interval because f prime is equal to 0 at one point on the interval. So we'll just say since f prime of x is less than or equal to 0 for this interval. All right. So that is the answer to question number 2. We know our extrema, or at least where they occur, and we know where the function is increasing or decreasing. So let's go ahead and go on to answer question number 3. I guess before we do that, let's go ahead and bring up the answers to number 1 and 2 just to make sure we're all good here. We can see that, just to recap, f prime is equal to 0 at 0 and 3, so those are my only critical points because f prime exists everywhere and there's no endpoints. We checked the signs of f prime, we got negative, negative, positive, so we can see that we have a relative minimum at 3. It's also an absolute minimum at x equals 3 for that justification. We can see that f is increasing over the intervals for which f prime is positive. We can see that f is decreasing over the intervals for which f prime is negative. Now let's go ahead and go on to concavity. Concavity deals with the second derivative like we talked about yesterday. So I'm going to go ahead and erase everything about number 1 and number 2. And because we're looking at concavity, we have to take the second derivative here. So we'd say f double prime of x. This is just a power rule derivative, so that'd be 12x squared minus 24x. We're going to go ahead and factor this. So we end up with, we're going to factor out a 12x. We're left with an x and a minus 2. Now, there's our second derivative. In order to know when the second derivative is positive or negative, we're going to do the same things that we did when we were asking where the function is increasing or decreasing. We're going to set our second derivative this time equal to 0 instead of our first derivative, and we're going to go ahead and solve this. Now, I do want to emphasize this. This is very important in terms of expressing your work, and AP readers look for this. If you don't set f double prime equal to 0 and you just skip that step altogether, so if you just say from here x equals 0 and x equals 2, you're not going to earn all your points. They're going to want to know where or why x equals 0 and 2. Well, the reason x equals 0 and 2 is because we were looking for the zeros of f double prime. So we have to express that. If we don't, we're going to be losing points. So that occurs at 0 and at 2. And then from there, we would set up our number line just like we always have at 0 and at 2. We have zeros for our second derivative. So f double prime is 0 at those. We're going to go ahead and plug in values, x values to the left and to the right of each of those. So we'll plug in like -1. If I plug in -1, this becomes a negative times a negative. That's a positive. If I plug in 1, this is a positive. This will be a negative, so it's a negative. If I plug in 3, I've got a positive times a positive, which is a positive. So just recapping a little bit here, I think this is kind of a nice thing to do. Because f double prime is positive, we can now say that f is concave up. And then since f double prime is negative, f is concave down, and so on. So we can just draw an extra part of our number line so we can see what's going on here. And we can answer this question pretty easily. We would say, for number 3, f is concave up over the interval negative infinity less than x less than 0, and 2 is less than x is less than infinity, since f double prime is positive. Okay? And then we can also conclude that f is concave down over the interval 0 is less than x is less than 2, since f double prime is negative. And I should probably add to that, negative over this interval, positive over this interval, or these intervals. So that answers question number 3. And now I'm gonna add a question to this. I'm gonna say question number 4, identify the points of inflection, or identify where the points of inflection occur. Well, that's pretty easy. Points of inflection occur when f double prime changes signs. So we would say points of inflection occur when x equals 0 and 2, since f double prime changes signs at these points. Okay, so that wraps up this lesson. Pretty basic lesson, pretty short, I think. Now, I would add to this, on my website, I do have a great practice activity that relates the ideas of the number lines of f prime and f double prime to the graph of f. So if you want to check out my website and click on this lesson Lesson, I believe, 4.8. There's a matching activity there that might be beneficial for you to better understand how F prime, and F double prime relate in regards to number lines and graphs. So I hope that helps you out. I hope that you gained insight into the world of calculus, and I'll see you again next time.